Go.
Okay, so let's talk about then concave versus convex mirrors. So we saw on that last slide, so this was our last slide, we had this one as concave, we had this one as convex. So concave mirrors act as converging mirrors, and that just means that they're going to bring light together. They're going to converge light. They focus it at one point. So let's go back and look at that picture. So this is my concave mirror. I know it's concave because it's like caving inward. I have my light hits that mirror, bounces off, goes through this point. Hits that mirror, bounces off, goes through the same point. Hits that mirror, bounces off, same point. Hits, bounces, same point. Hits, bounces, same point. So that has to be a converging mirror because all light rays are coming together after hitting that surface. Convex mirrors then will act as diverging mirrors. So what that means is the light rays are actually moving very far apart. They're spreading out from one another. So let's go back to that picture. Here's my convex mirror. So I know it's convex because it's more curved outward. So I have my light ray, it hits, goes out this way. Light ray here hits, moves in a totally different direction. Light ray hits here, moves straight back. I hit here, moves out in a completely different direction. Hits here, again this one points in a completely different direction. These light rays had to have come together at some point because we see some type of image. So that means we can do some line tracing, some ray tracing. We can add those dashed lines to see where maybe those light rays would have come together, where it looks like maybe they'd come apart from one another, and that would be right here. So because the light isn't actually converging or coming together once it hits that mirror, this has to be a diverging mirror. So usually these mirrors will produce virtual images because this image really isn't real. Our brain pretends like it's really there when it's not. Again, we talked about focal length the last time, and the focal length is just the distance from the vertex, which we're just calling that the center of the mirror, to the focal point, and that's where all of those light rays come together. So let's look back at this again. Here's my focal point. There's my middle of the mirror. That means the distance between those 2 points. That's my focal length. If I look at this one, here's the middle of my mirror. There's my focal point. The distance between those two things would be my focal length. We symbolize that with a lowercase f. For mirrors, and this is only true for mirrors, this is the only difference between mirrors and lenses. For mirrors, the focal length is equal to the radius of curvature divided by 2. So for mirrors, our focal length will always be half the radius of curvature. And that's just one of these fun little formulas. They will never give you that on your AP test. They won't give you that on your formula sheet. They won't give you that on your multiple choice. So this is something that you're going to have to know when we talk about mirrors. Focal length equals the radius of curvature divided by 2. And I think this will make much more sense as we do an example. Okay, so of course we can find or locate images based on something called ray diagramming. And when we do ray diagramming, we always draw 3 rays. Always draw 3 rays. So these are the rays that they've done together. So we have a parallel ray. These are our parallel rays. This is something they call a chief ray. I don't know why they don't have that third one there. I guess our third one is in here. But the 2 that are most important are our parallel ray and our chief ray. On our parallel ray, let's just draw this out. We're going to first start with a converging lens. So that's a concave, or not lens, a concave mirror, converging mirror. Okay, so I know that this is my concave mirror. I know it's concave because it's bent inward. So I know this is a concave mirror. I'm going to call this line has a certain name. Do you remember what it's called? Jonathan, what's this line called?
See? The axis thing.
Axis. Optic axis.
It's C, isn't it?
optic axis. See center of curvature. Okay, so my line here, there's my optic axis. I'm going to draw in an object. So in this picture they use a candle. I can't draw, as you all know. So it's just going to be a little person. Should I make him prettier?
Girl made a girl, your hair. Okay, no, she's fine.
Oh my gosh!
She needs to definitely go on Atkins.
Jonathan, stop.
Go on Atkins. Or Mary
I know
Atkins.
Michael, we're good, I can't draw, so.
Or Mary Atkins.
Okay,
What is it?
here's my person. I'm just going to designate a focal length, or a focal point. So I'm going to call that my focal point. And then I know that my center of curvature is going to be twice that of the focal length. So maybe let's say that'd be twice the focal length. Does that look about good? It's about half of that. Okay. And then here's my object. So first ray that we're going to draw is called the parallel ray. And this parallel ray, it just means that I have a ray that is parallel to the optic axis. So I'm going to draw my first ray. It's parallel to the optic axis. Once it reflects, or when it bounces off, it's going to go through the focal point. So this is the first ray. Parallel to the optic axis, it hits the mirror, always goes through the focal point. This is always true. Next one, I have a chief or radial ray. In the picture, this one ends up going through the center of curvature, and then it's going to go straight back through. So on this one, I have a light ray. It's going to go through there, and then it's just going to continue to bounce back and forth and back and forth. So that's my second type of ray. So this would be number 1. This would be number 2. Now typically, you can find where the image is just in those 2 rays, but we like to use 3 just to make sure like it's a triple check for us. So it's just this nice way that we can absolutely know for sure where the image will be located. So this last ray that we're going to do, it's going to be the opposite of our first ray. So our first ray went parallel to the optic axis, then through the focal point. Our third ray is going to end up going through the focal point, and then it's going to go through, then it's going to go parallel to the axis. So let's try this one. So this would be number 3. Okay, my goal is to find where all 3 of those rays intersected with one another. I don't see that anything's intersected here. I only have 2 lines. I don't have anything where I see where all 3 lines have come together is right here. So that's where all 3 of these lines came together. That means my image has to be located right here. Since it's under the optic axis, it has to be inverted. There's no way it could be upright. The only way it could be upright if it were above the optic axis. So that means that I'm going to see I'm going to see what Jonathan calls a fat woman. Upside down. Do you think that that one looks smaller or larger than the original? Looks smaller. So in this case, this one looks smaller. But this is using ray diagramming so that we can locate our images. Okay, so we're going to do lots of practice with this on Monday. So I would like you, if you could, actually,